Hello Northside students, this is Kyle Munyon here to help you with the pre-calculus fall semester exam for 2016. This video is going to include questions 1 through 6 of the review. So let's go ahead and get started on these. Alright, on questions 1A through C, we're asked to do some transformations from some parent functions. If you're not familiar with all of the parent functions, I would suggest that you check your notes. If you took some notes on parent functions, you should have the ones that we're using in class. If not, you can just go online and find a list of parent functions as I've printed up here. Hopefully, though, you do have some notes on them already. So first we need to recognize what each of these equations parent function is, so then we can do the transformations from there. All right, on question 1, I recognize that this is, the function that's happening is e, a constant value, raised to an exponent. So the parent function is exponential. So I need to know not only what that looks like, but also maybe a couple of important points to be able to transform them. So some easy ones to graph are always like when x equals 0. We can see what that point is. So I can plot the point, oops. One easy point to plot is when f equals 0 and when x equals 0. We should be able to plot that one pretty easily. So we evaluate f of 0, and we know that anything raised to the power of 0 is 1. So we should have a point at 0, 1 that we can plot. And also if I plug in a 1, e to the first power is approximately 2.718. So I should be able to plot both of those on the parent function relatively easy. So I'll go ahead and plot those 0, 1, and 1, 2.78 is approximately right here. Also, I know that I'm not going to be able to turn this into a negative value, even if I had negative exponents. It's just going to keep getting closer and closer to 0. So it's going to be approaching the x-axis right here. And you can tell that from the parent function graphs in your notes or the ones that you looked up online. All right, so let's do our transformation now, one piece at a time. The first thing that's happening to our x values is being subtracted by 3. So we know that if that's happening within the function, not before or after the function, that means that it's going to be translating it to the right 3 units. So I know that each of these values should get translated to the right 3 units. 1, 2, 3. 1, 2, 3. From there, this multiplying by 0.5 before we add 2, following the order of operations, tells us it's going to be a vertical compression by a factor of 0.5. So all these values should be compressed towards the x-axis. So this 1 is going to become a 0.5. And this 2.718 should be about a 1.3, somewhere around here. So I'm going to get rid of those other values that we translated to the right. So we're just left with these two. And then we'll do the last translation. Adding 2 just means that's going to translate up 2 units. So 0.5 is going to go to 1.5, 2.5. And 1.3 is going to go to 2.3, 3.3. And since originally it was approaching the x-axis, or approaching the function value was approaching 0, I know that asymptote where it's approaching needs to be moving up 2 units as well. So I know that when I transform this function, it's going to start very close to y equals 2 and go through both of the values after those transformations. All right, so this was our original function. And this, let's call this g of x our transformed function. Question number 2, we're going to do the same way. Try to move a little bit more efficiently now since we've already talked about parent functions. On question number 2, I recognize that this is a square root parent function. Same thing. Recognize the parent function. I look it up on my graph just to make sure I remember what it looks like. Square root parent function, couple of points that I can plot. Square root of 1 is 1. And something like square root of 4 is 2. So I can plot those points 1, 1. I guess 0 is another easy one that we could plot. Square root of 0 is 0. So if I start with my parent function, 0, 0, 1, 1, and 4, 2, should look like this. This is the inverse of quadratic. Should have our parent function. From here, we only have a couple of transformations. Because this 2 is applied within the function, we know that's going to be a horizontal translation that we're remember, horizontal translations are always the opposite of what they appear to be. If it says x plus 2, we know that's going to be a translation to the left 2 units. So I'll go ahead and do this one also, since this is happening after the function is applied, after the square root. I know it's going to be a translation down 3. So on each one of these points that I plotted already, I need to translate to the left 2, and this means down 3. All right, so 1, 2, 1, 2, 3. 1, 2, 1, 2, 3. 1, 2, 1, 2, 3. All right, so this will be our original function, and this is our transformed function after a translation to the left 2 units and down 3 units. All right, the last question we're doing is the natural log function transformed, and same thing, we need to look on our parent functions. If you don't remember them, find out that the log or natural log parent function will look like this. If you forgot, natural log is just a regular log with a base of e. So let's go ahead and write down, just like we did on the other couple of questions, a few points that we can plot. So if I have the function f of x equals ln x for the parent function, this one, if you saw on the parent function graph, is not actually going to be touching the y-axis down here. Just like the inverse exponential got really close to the x-axis and never touched it, you couldn't make it equal 0. Well, same thing. If you tried to evaluate x in this function at 0, you can't get a value. That's one of the log properties that doesn't allow you to get 0 in there. So let's try a different one, like 1. F of 1. Basically, in case you forgot, a log is saying this base raised to some power should give you this. So what do I have to raise e to the power 2 to get 1? Well, any number, e is just 2.718, can be raised to the power of 0 and give you the value of 1. So if I evaluate this, I should get 0. So I know when I plug in a 1, I get 0. Using that same method, I should also be able to evaluate e, because I know that log base e raised to what power equals e? Well, it didn't change, so it should just be to the first power. So when I plug in e, or 2.718, I get a 1. So those are some points that we can plot on our graph. So let's go ahead and plot 1, 0 in our parent function, and about 2.718, 1. And obviously this is already curving like we thought it would towards the negative y-axis down there. All right, so this is very confusing for some students because it does look very similar to the square root parent function, but obviously it's not the same. This one definitely does have negative values. It's got this part here is the same shape, but think of it as the inverse of the exponential function. It's a better way. It's got to be approaching the negative y-axis here, just like exponential approaches the negative x-axis. All right, now that we have our parent function, we have those points. The only transformation that's happening is happening before the function happens, before the natural log function happens. So I know that's a translation in the horizontal direction. X minus 1 means that it's going to be translated to the right 1 unit. So I translate this one and this one, 1 unit. And I know that where it's approaching the negative y-axis, it's also going to translate to the right 1 unit. So once again, we have f of x, our original function, and after it's translated to the right 1 unit, I have my transformed function g of x. All right. Let's move down to question number 2. Basically, it's just asking you to make sure you know the logarithmic properties. So I guess I'll just write on this paper. This one. So the product properties, the logarithmic product properties, says that when you have a log with some base b, and then of a product, so let's say m times n, this is the examples that they used in the book, that is equivalent to the sum of those individual factors logs with those bases. So log base b of m plus log base b of n, which is good to know because this works both ways. Sometimes you have to combine the sum of logs with similar bases to be able to solve an equation. I think later on in this review there's a couple questions that you do need to do that. The quotient property is the exact opposite. If you have the log base b of the quotient, you're going to subtract these. So let's go ahead and write that one down as well. Log base b of m divided by n is equivalent to log base b of m minus log base b of n. The power property is one of the most commonly used and easiest understood ones. The power property says that log base b of m to the power of n is equal to, we can take that exponent and put it out in front of the log, n times log base b of m. And the last one it's kind of common sense, but it's often overlooked. And same thing, this property is used later on in the review. The equality says that if log base b of m equals log base b of n, then m and n have to be equivalent values. All right, one that's not listed on here that we didn't use as much because our calculators allow us to not have to use this one is the change of base rule. If you have a base that's not convenient to use, like sometimes you need to change a base to 10 if you're using a scientific calculator, there is a change of base rule I want to make sure you guys are familiar with. So let's say you have log base b of x, and let's say this isn't a convenient base. Let's say it's anything other than 10 or e. You can change it to whatever base you want and just take the quotient of a couple of logs. So that's equivalent to log whatever base you want. I'm going to put a 10 here just because that's a commonly chosen base of x, over log base 10 of b. So basically, your base goes in the denominator. What you're taking the log of goes in the numerator. So this kind of goes up here, this goes down here, and you can choose whatever base you want here. All right, so number 2b, if you want some more information on these, I think these are found on page 62 through 65 in the book. The Springboard book. All right. I know that ln8, as I mentioned on question 3, natural log is really just log base e. So the very first way I could rewrite this is as log base e of 8. And one thing you could do from there, the change of base rule, is you could rewrite this as log whatever base you want of 8 over log base 10 of e. If you wanted to, break this one down into some other values, you could break this one down. You could rewrite this as log base e of 2 times 4. So that would be the product rule here that says we could write it as the sum of 2 separate logs. You could really use any of these that you wanted to. You could write this as 2 to the power of 3 and then rewrite that using the power rule here as well. I'll do that one in just a second as well. And let's just practice one more on here just to show. All right, lots of different ways that you could write these. Using log, natural log, doesn't really matter how you do these. You just need to be familiar with the rules because if you need to solve an equation, there's a good chance you could have to use 2, 3, 4 of these at the same time on one of your equations. All right, question number 3. All right, on question number 3, all we're doing is identifying if functions are even, odd, or neither. So more than anything, you just need to know the definition. Even functions are symmetric about the y-axis, and odd functions are symmetric about the origin. All right, so let's use that information to help us determine. Notice we do have an option for neither on some of these. Some students have the confusion of just saying I can tell by the power or the end behavior what the degree is and say, okay, if the degree says that it's a fourth degree polynomial or an even polynomial, then I know that, oh, that means that it's even. When in reality, it needs to be symmetric about the y-axis or symmetric about the origin. So this first one I see is a mirror image across the y-axis. So this one is definitely even. This one is symmetric about the origin. Each point is reflected directly through the origin. Notice this point here reflected directly through the origin, any individual point. Another way to do that is to rotate it exactly 180 degrees, and I see it looks the same. So you can think of odd functions as rotating 180 degrees. This one, notice, is not a mirror image. So this one is not symmetric about the y-axis. If you also went through the origin, there's nothing down here, so this one is neither. Question D, this one's a little bit tricky. What I would recommend doing is picking, a clearly non-already symmetric function and evaluating and see how they compare to each other. So let's say like the square root parent function. The parent function looks like this. What happens when I make the x values negative? Just the x values. Well, I'll take all these positive and make them negative. It's going to look like this. So if this is f of x, this is going to be f of negative x. And what happens if I take all of the function values and make those negative? So the value of the function becomes negative. That's going to be a reflection over the x-axis. It's going to look like this. And I see very quickly the dotted line I've created is symmetric about the origin. So if those values are equivalent to each other, that means that this is odd. I can do the same thing for this one. If I take my original parent function of the square root, if I make the x values negative, that's just going to look like this. So those two functions compare to each other. They are symmetric about the y-axis, which means they are even. Last one, I see that all that's happening right here is regardless of the x value, the y value stays the same. If I was to plot these, looks like it's going to be symmetric about the y-axis. Every negative x value has the exact same positive x value on the function. All right, so that one's symmetric about the y-axis, so this one is even as well. You could graph it, easiest way to check, or you could just check to see what's happening right here. Looks like the negative x values are exactly the same as the function's original x values. So when you make this x negative, the value of the function is still the same. So that's why these are actually the same type of question here. All right, question number 4. All right, so here it's asking us to write an arithmetic sequence and a geometric sequence for these given values, given a couple of terms in a sequence. So we know a sub 1 is 8, a sub 2 is 4. Let's write the expression for the nth term for an arithmetic sequence. Well, the general arithmetic sequence formula, the explicit formula to be able to find any term number, is always going to be a sub n equals the first term, a sub 1, plus the term number minus 1 times the number of, times the common difference. Hopefully that's a formula that you guys have memorized, but it's not hard to derive if you think about it. You can always just ask yourself, okay, after the first term, I need to add one common difference. So let's say you have 8 and then 4. If this was an arithmetic sequence, you're subtracting 4 every time. So after your first term, on your first term, you don't have to add or subtract any common differences. But on your second term, you have to add one common difference of negative 4. On your third term, you're adding 2. So the number of common differences that you're applying is always one less than the term number. So on the first term, you're adding 0 common differences. On the second term, you're adding 1. That's where the n minus 1 comes from, and that tells you how many common differences to apply. All right, so it should be easy to plug in here. And the common difference is negative 4. Okay. On a geometric sequence, the explicit formula for a geometric sequence is going to be a sub n equals the first term times the common ratio to to the power of n minus 1. So on this one, geometric sequence we know is being increased or decreased by a common ratio. Obviously, if r is greater than 1, the sequence values are going to be increasing. If r is in between 0 and 1, the sequence values are going to be decreasing. So just like before, how many times do we apply this ratio from the first term? Well, in the very first term, you don't want to multiply by the ratio any times. So when you plug in a 1 right here, you get 0. R to the power of 0 is 1. It's not going to change your original term. But after that, let's say, if you're cutting this in half every time, with a geometric sequence, we have 8, 4, 2, 1. Notice we applied the common difference of the common ratio of 0.5, or cutting it in half, 1/2 or 0.5, once. So even though it's the second term, we've only applied the common ratio once. I guess I should also talk about how to get a common difference or a common ratio. I'll go ahead and do that one. To find a common difference, you take any term number and subtract the previous term number. So let's say I wanted to find this common difference. Okay, so I take a term number like 4 and subtract the previous term number, which would be 8, and I would get negative 4. To find a common ratio, you do the same thing but with dividing. To find a common ratio, you take any term number and divide by the previous term number. So let's take our term number 4, divided by previous term number would be 8. Looks like we get a common ratio of 1/2. 4 divided by 8 is 1/2. All right, so we have written an arithmetic and a geometric sequence. On question 5, it says find all the asymptotes of the following function. Although it may just be asking about the vertical asymptotes, we'll go ahead and find the horizontal one as well. So if you wanted to think of this as a rational function, because you do have a variable in the denominator, you could do that. You could go through radii. So I'll just go through the A and E part of radii, the asymptote and end behavior, to be able to talk about this question. So this will give us our vertical asymptote, and this will give us our horizontal asymptote. All right, so how do we find the vertical asymptotes? If you look on your radii's notes page, hopefully you took one or have one with you. To find a vertical asymptote, you just set the denominator equal to 0. And solve. I guess I'll do that right here. So I get x equals 3/2 is going to be the equation of our vertical asymptote. All right, so that's the only factor down there, so I don't need to set anything else equal to 0. Find any other horizontal asymptotes. For any other vertical asymptotes, for the horizontal asymptote, I need to check and see if the ratio is top heavy, bottom heavy, or balanced. I see that I have an x to the first power and an x to the first power in both the numerator and denominator. So that means that it is balanced. So I need to look at the ratio of the x values, leading x values coefficients. So I have a 3 over negative 2, which means that I'm going to have a horizontal asymptote at y equals negative 3/2. And I got that from the coefficients. When the ratio is balanced, the degree on the top and the bottom, or the numerator and denominator, is the same. You just look at the coefficients on the leading term. So 3 and a negative 2 tells me that is going to be the horizontal asymptote. All right, question number 6. What are the first 6 terms of the sequence a sub n equals 9n plus 5? That seems really straightforward to me. Just evaluate each one of these. So there is the first term. So all you did is evaluate. If you were allowed to use a calculator, it'd be real easy just to type this in as a linear function and check the table. When x equals 1, the value equals 14, so forth. You're not using one on this. You could either evaluate each one, or some students would just find the first term and then use the common difference and add 9 every time. Doesn't matter how you do it, as long as you recognize what the common difference is in this equation, because as n changes, you're going to change the amount of times that you're applying that common difference of 9. So it could be 1 9 added, or 2 or 3. Obviously, as the terms increase, you're adding 9 more and more and more. Number 7, let's write a function in both factored form and expanded form that has these asymptotes. An x-intercept at 2, 0, a whole at 3. This one is definitely a challenge for a lot of students, but I really like these types of questions because it really tests to see if you know everything you need to know about these. Writing your own equations, both graphing and writing an equation from a graph. Good exercises. So let's start piece by piece. Let's say it has an asymptote at y equals 3. Well, this is a horizontal line at y equals 3. And the way that we get horizontal asymptotes is from the end behavior. So I know that the end behavior is determined by E on the Radies notes page. It's either balanced, top heavy, or bottom heavy to give us, to tell us if we have an asymptote. The only way it has an asymptote is if it's balanced or bottom heavy. If it's bottom heavy, the asymptote is at 0. If it's balanced, you use the ratio of the leading coefficients, leading terms coefficients. So that means that I have to have a 3 over 1 to start off with. All right? And then when I'm done, I have to make sure that my equation is balanced. So, obviously I need to make sure when I'm done that if I have an x over x to the first power, that they're both the same power, or x squared over x squared. So let's keep on trucking, and then we'll have to come back to this one just to make sure that it is balanced. Next thing, it says that we have an asymptote at x equals 1. And that's a vertical asymptote. That's A on the Radies notes page. And that's determined by setting the denominator of your equation equal to 0. So to have an asymptote at 1, you have to have a factor of x minus 1 in the denominator. So this part gives us an x minus 1 in the denominator. The next thing says that there's an x-intercept at 2, 0. X-intercepts are the roots, or R part of radii. So that means to find a root, you would set the numerator equal to 0. So to have a root at 2, 0, I have to have a factor of x minus 2 in the numerator. If I set that equal to 0, I get a root of 2. The last thing it says is we have a hole at x equals negative 3. So when x equals negative 3, there would be a hole in the graph. So this isn't an asymptote, but if wherever the function's at, there does need to be a hole in the graph here. We're not making the graph, but if we were, we would need to indicate that there is a hole there. And holes are created when there's a factor in the numerator and denominator that cancels out. So if the hole is at negative 3, that means the factor would be x plus 3. Alright, so it looks to me like we have finished each piece of this. And when I get done, I see that in my numerator, my leading terms coefficient would be a 3, and the degree would be 2. So I'd have a 3x squared. In the denominator, I'd have a 1x squared. So they are balanced, and I do have a ratio of 3 over 1. So just to go back and do that last step to make sure I did it correctly, then I do see that it is balanced, and I have a ratio of 3 over 1. It did ask to write both the expanded and factored form, so all you need to do is multiply these out. So I'll multiply the two factors here first, and then multiply the 3 in to do that. So 3 in the denominator, I don't really need to distribute that 1. So alright, so you could say you're done here, or you could distribute the 3 to each one of these. So there's an expanded form, and here's when we had it in factored form. Obviously, if you were doing this one on your own, you could check your work here or on your calculator. This is not a calculator section, but you should feel pretty confident after practicing a few of these. Number 8, really easy question. What is the maximum possible number of zeros, maximum possible number of turning points, and y-intercept for the polynomial? The maximum number of zeros can always be determined from the degree of the polynomial. So max number of zeros is going to equal 4. And we get that from the degree. The max number of turning points is always the max number of zeros minus 1. So if the degree is 4, that means there can only be a maximum of 3 turning points. Don't overthink that one. It's always going to be 1 less than the number of zeros for the maximum number of turning points. The last thing is y-intercept, also pretty easy. To find the y-intercept, you just make x equals 0, or evaluate the function when x equals 0. And all of the terms with x are going to turn into zeros. You really don't need to write this part out. The only thing we're going to end up with is this negative 1 here at the end. So your y-intercept is going to be at 0, negative 1. And obviously all of these 0 plus 0 minus 0 plus 0 minus 1, you're going to just get the value that doesn't have an x on it as your y-intercept, just like a linear function. This number that's added or subtracted at the end, or a quadratic, will be your y-intercept. Okay. Next page. On question number 9. A relatively easy question, but I can see how the answer choices may confuse a few of you because they're all so similar. It says a new boat is purchased for $16,800. It depreciates continuously at a rate of 18%. Which of the following exponential functions represents the value of the RV after T years of ownership. All right, well, we see that it's asking for the value, and the value obviously means that it's going to be worth money. So we should recognize that it's going to be a positive amount here. Should be answer choice A or B. And the question is not asking which one represents the amount owed, if you like bought it on a loan or something. So we're not going to get a negative value. Should be a positive value. And then the equation that they're using is the principal amount times e to the rate times time, or a lot of you guys may know it as the PERT equation. And the rate, if it's depreciating, means we're losing 18%. So you can tell here on each one of these that it is a negative 18 of some sort. And percent converted to a decimal should be 0.18. So looks to me like, since we've already narrowed